Stengel from University of Hawaii, and we're working on several aspects of WIMP dark matter. And today is going to tell us some variations on WIMP. So let's welcome him.
Thanks for the introduction. Thanks everybody for coming for Texas A&M theme, so that's cool. So I'm going to talk about a few different projects that I work on that are ongoing collaborations with these people. And they're basically everyone's kind of weird pet dark matter project that I've gotten to work on. And so just the overarching thing is that they're all phenomenology, and the resulting experimental signatures are just sort of a little bit different from what you would normally look for in a sort of typical WIMP dark matter scenario. So I'm briefly just going to motivate normal WIMP dark matter and sort of outline how the sort of things that we're looking at are slightly different. So in particular, the three projects I'll be talking about are looking for light dark matter in bound state decays at high luminosity colliders. I'll also be looking at, within the MSSM, sort of a strange part of parameter space where you get spin-independent scattering through strange quark mixing. And then lastly, if I have time, I'm going to talk a little bit about multi-component dark matter, dynamical dark matter in particular as an example, and how it applies to constraints of the early universe, with an example in light element abundances. So, one of the best motivations for new physics at the weak scale is the WIMP miracle. So if you just have a stable thermal particle that's annihilating, it's going to freeze out with some relic density that goes like 1 over the annihilation cross-section. If you have a weak coupling, then just dimensionally you know that you're going to wind up with a cross-section that goes like 1 over the dark matter mass squared with some velocity dependence. And if you make that mass weak scale, you get something that looks like this plot over here, where this brown band is basically the dark matter mass range that you can get, a percentage of the observed dark matter abundance that you see today from WMAP of Planck. And the idea is just at the top of this plot, you get a weak scale of dark matter mass, right? And so this is just kind of a cartoon, right? The band can be bigger or smaller than that, but just in general, it's WIMP miracle. Also, you can look at it the other way. Just say you're motivated by new physics at the weak scale from sort of new models of new physics. So if you want to stabilize the hierarchy problem, for instance, you're often going to introduce new weak scale particles. If you have something like extra dimensions or supersymmetry, you're going to have something that's a discrete symmetry, so either R parity or KK parity, that stabilizes your lightest new particle, and that gives you your WIMP candidate. So in the MSSN in particular, you'll typically have a mixture of gauginos and Higgs-inos, and depending on where you are in the MSSM, you get different interactions. So for some set of soft SUSY breaking parameters, you get pictures that look like this. The green bands are sort of where you're getting the right relic density. The blue contours are your neutralino mass. So basically you're seeing that you get weak scale neutralinos as you cross the blue contours over the green band, satisfying the relic density. This is also just sort of a cartoon you can always show, just how you detect dark matter. And so this sort of outlines a little bit each topic of my talk, sort of how we look at things a little bit different from what you would normally look at. So at colliders, where you're making dark matter, you typically have something like monojets or jets plus mad Lhc. And we're going to look at epsilon decays at high luminosity colliders. We typically talk about scattering and looking at nuclear recoils. You're limited by your energy threshold for detecting those reflows, so a low mass direct detection isn't as helpful. Also, you have some large nuclear physics uncertainties when you talk about dark matter scattering, in particular for what I'll talk about, which is left-right mixing through strange quarks. And then for indirect detection, dark matter annihilating today, but I'll talk about lots of different dark matter fields annihilating in the early universe and changing observables, whether they're light element abundances or CMB ionization history. So first, the high luminosity stuff. Just as an analog to monojets, I'll just sort of outline model-independent constraints on effective operators, and then I'll go through these single photon decays of heavy quarkonium and then some results that we're putting out in the paper this week or next week, hopefully. But if you know that dark matter is interacting with the standard model and there's some new high-scale physics model that's mediating that interaction, as long as it's heavy, you can integrate it out, and you're just left with dark matter and the standard model interacting in some effective operator, right? And then you can just write down any kind of possible Lorentz invariant interaction structure that you can think of, right? So for fermionic dark matter, these are all the ones that you can write, that are dimension 6 or lower. What's also nice about this picture, besides being model independent, is that you can relate it to dark matter scattering. So you can take your results from monojet or upsilon decays and say, I can infer a limit on spin independent or spin dependent scattering. These different interaction structures will have different momentum and velocity dependencies. You basically want a 1 if you want to see anything, because you don't want it to depend on dark matter velocity. Similarly, if you annihilate an S wave, you can look for signals in indirect detection. Because again, if you're velocity dependent, then your annihilation cross-section is going to be suppressed. So these are just a couple of example plots from monojet searches at Lhc. But as I was saying, and these features are sort of common to any kind of collider search, whether it's monojet or, whether it's monojet or upsilon searches. But when you do these sort of model-independent searches, you become competitive with spin-dependent scattering, because in spin-dependent scattering, at direct detection, you don't have coherent scattering off of all the nucleons in the nuclei, so you don't have your A² enhancement. And so for monojet searches, you can see that you sort of probe a lower cross-section range. And also, you're not limited by the threshold of direct detection, so you can sort of push this mass range down a bit. And so if dark matter is living somewhere near this threshold, it's helpful to have these collider searches. Similarly, if you're annihilating through an S wave so these are like the D5 and D8 operators, there were F5 and F8 on the previous slide. This red line is the limit that you get from door spheroidals if you're annihilating the light quarks. And again, you see that you're not as threshold limited down in the lower mass range. Also, this plot in particular kind of tells you something nice, which is that if you have a thermal dark matter that's constituting all of your relic abundance, this green line is where your cross-section needs to be. So you know you need some other annihilation channels in order to deplete your dark matter enough to leave you with the correct relic density. So the usual monojet or monophoton diagram is sort of just this thing on the right. So we still have that, but we also just put in front of it the decay of a bound state meson. And the way these typically work is that you run at some excited state, which then has a hadronic decay or transition to your lower state, which then decays either to invisible or invisible plus a photon. You don't actually need this photon in the final state because you can reconstruct the the presence of the epsilon 1s in this picture just based on the dipion system. So at high luminosity colliders, you're really directly probing the coupling to heavy quark flavor, right? Which is different from monojet searches. Also, just a UV completion of this sort of comes naturally in models in the NMSSM, with a light pseudoscalar Higgs, mediating this interaction. And so this also complements monojet searches, because at least if you want to keep the matrix element unitary, you know that your mediator scale that's suppressing these dimension 6 or dimension 5 interactions, you need that to be around the characteristic energy scale of your process.
So our kind of sequences maybe I'll be with a photon with avatar.
So you just see two oppositely signed pion tracks, and then usually you can reconstruct at least the 1s peak from that. And then if you're running your single photon trigger, you have some cuts for just a single photon.
But there's a tremendous missing energy in this because of the dark matter. And so in this case, maybe you have jets, which corresponds to the pions. You have a single photon. So if you have just from the photon the missing energy, this is some signal that you can develop on the Stengel diagram.
Yeah, I mean, you need a lot of luminosity, right? I mean, so you're really setting so if you don't have the photon here, so that's maybe a simpler example, all you're really doing is you're running at some resonance for the 2s transition, and then you're looking for the oppositely signed pions.
And what kind of document mass are you sensitive to?
It has to be lower than the half the epsilon mass, right? So it has to be lower than 5 GeV. But yeah, you're really just trying to reconstruct the mass peak in the dipion distribution. And then if you have a photon in the final state, use the kinematics from that to reconstruct the mass distribution of the missing energy. But one other thing, and I'll get into a little more detail with that, is depending on your choice of bound state here and whether or not you have a pion in the final state, you sort of probe different interaction structures. Whereas at LHC, there's sort of broad categories of kinematic distributions, but it can sometimes be hard to differentiate in these model-independent searches between which operator you're looking at. So the effective operators are constructed by taking a standard model bilinear and a dark matter bilinear. And so your standard model bilinear tells you, is related to whether you're looking at a purely invisible decay to dark matter, or just invisible plus gamma. So if you are looking at a purely invisible decay, your quark bilinear angular momentum and quantum numbers have to match whatever those are for your bound state meson. So for an epsilon or a J psi, you would have JPC 1 minus minus. So you need a spatial vector index. So that's either the tensor bilinear or the vector one. When you add a photon to the final state, charge conjugation tells you that now you need a C plus in your quark bilinear. And so you'll notice that if you look at the C minus ones, which are vector and tensor, you flip that to plus, you're basically looking at all the other ones, so pseudovector, pseudoscalar, and scalar. And so just as a result for JPC 1 minus minus bound states, looking at purely invisible and invisible plus gamma, you actually end up looking at all possible dark matter standard model interaction structures. So a little bit more detail on that kind of idea is this table. So on the right, you just have kind of what I mentioned before, which is, and I just picked a few examples for operators that are relevant. So F1 and F8 are typically what you have in the MSSM for spin independent and spin dependent scattering. F4 would be your pseudoscalar Higgs exchange. But on the right, those columns are just the same from the table as before. But these middle two columns for decays with either purely invisible final states or the photon, you basically can relate different decays together, right? So upsilon decays with a photon are bounding the same operator as H sub B decays with a photon. Same operator is going to be bounded by chi B0 decays without a photon. Right? So you can, I mean, granted these channels are hard to measure because you need very large amounts of data, so these invisible decay widths are really only constrained for J psi and upsilon, but in principle, you can use different combinations of these to get a better handle on these sort of long lists of possible interaction structures.
So I'm still missing, what is that we actually detected in the detector?
So you're just using...
Has 2 pions, but there is no peak in the mass.
Well, yeah, you'll get a peak from, because you're...
It's a 3-body decay, so it's going to be between whatever, 500 TeV of the delta M.
No, but you're
It's not
making...
a narrow peak. How do you distinguish this from 1,000 of other pions which are in the event?
No, I mean, you do get a peak. You'll get a peak from, because it's a hadronic transition. You're not boosting the... So the center of mass frame for this guy is basically the same center of mass frame for this one. So the dipion system will give you a peak right around the mass of the upsilon 1s.
You have a distribution of that.
Yeah. So this is just for invisible decays. But just from dipion mass, you get the mass of the recoiling invisible system, right? And your mass peak over background, which is, so your background is this dashed line from things that you miss. But the mass peak gets reconstructed.
Maybe I have missed this. This is a plus and minus collider?
Yeah.
Sorry. Then I can get it.
Yeah. So, the one issue was that when you set limits on these decays with a photon in the final state, you have to basically simulate your signal using an angular and phase-space distribution for the photon based on one of these interaction structures. So that's just kind of how these limits from the R were published, right? So they really only showed results on limits on a branching fraction for decays to scalar dark matter with a S-wave dark matter standard model interaction. So for us, that's what we call our S1 and S2 interaction structures, which is this black curve. So in order to kind of approximate what the limits are for all these other operators, we want to basically, given the cuts on the phase space and the detector for the photon, define an efficiency for those cuts into that phase space on the detector by calculating a partially integrated branching fraction, dividing it by the fully integrated branching fraction, and if you multiply that number by this limit, it gives you some number that should be proportional to an observed number of events or not observed. And then to project back out the limits onto the other operators on the full branching fraction, you can define efficiencies for those and you get the curves that you see. And obviously they don't change that much, and this is just an approximation. For instance, it doesn't take into account, you could have some change in efficiency within the phase space considered in the analysis, but we don't really consider that. The Energy threshold turns out not to make such a big difference in this approximation. So the photon detection threshold. The cuts you make on the scattering angle are what's giving you your little bit of wiggle here. So that turns out to play kind of an important role, or more important than the energy threshold. But now you can turn this around and limit your interaction strength or the suppression scale for your operators. So on the left, you have operators that are mediated by scalars or pseudoscalars. And so sort of the standard assumption you make here is that you're coupling to quark mass. And so for upsilon decays, that sort of enhances these limits relative to monojet limits, because our coupling is going like a B quark mass instead of light quark masses from the PDFs. So you sort of see that for F1, for instance, this green curve is at least getting into the same ballpark as what you get at monojet searches. Whereas for pseudovector coupling, you just sort of assume that you're coupling to some charge and you go like 1 over lambda squared, right? And then your monojet searches are just putting mediator scales way up here, and the upsilon searches are much less efficient. But as I described, they're sort of complementary in a few different ways, even if they're not making as much of an impact on the actual scale. So the last thing you can show this sort of thing is you can turn that plot upside down for things that allow for velocity-independent scattering, and this is spin-independent scattering. So this is sort of a factor of 1,000 removed on the horizontal axis, what you might normally show. This is low-mass dark matter. So the signal regions and CDMS and Lhc limits are these curves on the left. And the 3 sets of curves down here are for scalar, fermionic, and vector dark matter. Vector dark matter, the constraints are enhanced at low mass because of the longitudinal polarization of the dark matter particles. Also plotted here is so we have these solid curves and dashed ones. The solid curves assume that you're coupling to all quark flavors, but since all we know for sure is that we're limiting our coupling to bottom quarks. Basically, if you only consider scattering cross-section, coupling the bottom quarks through heavy quark loop, which accesses the gluon content of the nucleon, you wind up with a slightly more stringent limit, but you're only considering, basically you have 1/6 of the matrix element that you had for the solid one, you square that. So that's why the constraints look a little bit tighter, but you're only considering scattering through bottom quarks. Strange Brew and the Incredible Bulk, that's sort of an amalgam of paper titles from this sort of project that I'm working on with Jason, Pearl, and Chris. But I'll sort of talk about relaxing minimal flavor violation in the MSSM with Mino dark matter, how spin-independent scattering changes when you do it through strange quark mixing, and then I'll talk about some possibilities for sensitivity to direct detection. So usually, just as an example, in MSUGR or the CMSSM, you have something like unifying Gravitino masses, or at least a low Vino mass relative to Wino. And that tells you have small Wino content. And so if you assume minimal flavor violation, you know that you don't have diagrams that give you S-channel annihilation through fermion mixing. So you need some Higgsino content to give you diagrams like this, which have some Higgsino eigenstates, in order to get a high enough S-wave annihilation cross-section. And so if you take this one, turn it on its side, it tells you something about spin-independent scattering. Right? Typically, you'll talk about Higgs exchange. Right? But I sort of mentioned this in the last section, but the scalar-mediated interactions are velocity independent. You're coupling to some quark mass. If you have minimal flavor violation, right? You'll have diagrams like this one and just fermion exchange. These diagrams are typically, these fermion exchange diagrams are typically suppressed because of LHC data and just the Higgs mass. Basically, you're pushing your fermion masses up above the TeV, so this mediator is going to suppress the contribution of those diagrams. We can consider something a little bit different. So the bulk region in the MSSM was something people used to look at. It had light fermions and pure Reno dark matter. We sort of have a new bulk region where we relax minimal flavor violation, and so pure Reno dark matter needs left-right mixing through some fermions for S-wave annihilation. You need something relatively light, so you can't do it through squarks unless you're in some kind of weird region. But you can do it through leptons, through diagrams like this. But if you start introducing left-right mixing into the MSSM, you have to make sure that you meet dipole moment constraints, because you'll start giving contributions to those. This is all sort of in the incredible bulk paper, which is this one. But I worked on the spin-independent scattering, which is through left-right squark exchange. And so if you have one degenerate squark flavor, I have a few slides about Lhc constraints. Instead of being at around a TeV, your squark mass is really just constrained to 400 or 500 GeV for decoupled gluinos. And then as your gluino mass comes down, the T-channel gluino contribution is going to contribute to the production of first generation squarks more than it does for second, right? So the constraints are going to increase for first generation and not for second. Also, instead of coupling the mass, now you have a pure gauge coupling that's proportional to the mixing. So LHC constraints, just in JETS plus net searches, you can sort of think of them a few different ways. If you're in CMSSM, right, there's some selection of self-SIGI parameters. The point of this plot is that your squark mass has to be larger than a GeV, or TeV rather. Similar story, but if you only consider production of light squarks, so if you have 8 degenerate light squarks, again, your mass limits are pushing right around a TeV. If you allow for one non-degenerate light squark flavor, you get down to 400 or 500 GeV.
So, on this one,
Yeah.
you mentioned this about 500 GeV constraints. So what is it, how much mass is that, and how much that parameter is into?
So what is the dark matter mass? I mean, so the constraints really only come in.
Oh, so that to 500 is a private constraint, not your detection constraint.
Right.
Oh.
Yeah. So the LHC constraint is putting you at 500 GeV. The dark matter becomes unconstrained as you increase the LHC mass. Sort of this PDF effect when you bring the gluino mass down, sort of illustrated in these two plots. So for first generation squarks, as you bring down the gluino mass from up here, the constraints sort of strengthen on your first generation squark production. Whereas for second generation, it really doesn't change very much between decoupled gluinos and one gluino mass. So that's kind of why we look at train squarks. And the reason why we don't look at charm squarks is because the scattering cross-section will be suppressed by the charm mass. I'll talk about that here, or in the next slide. So there's a little bit of nitty-gritty here to talk about it, spin-independent scattering. But I sort of get into it because the uncertainties in spin-independent scattering that are always there become even more important in a situation like this. So if you write your spin-independent scattering cross-section like this, you can define your integrated nucleon form factors here and calculate them based on measuring sigma pi n, which you get from pion nucleon scattering, and the strangeness content of the nucleon, which is this y, or equivalently measuring sigma naught, which you calculate from chiral perturbation theory. And so you can get wildly different answers for the size of sigma naught depending on what order you go to in chiral perturbation theory. Also, sigma pi n, you can measure it, but it has some very large uncertainties. Okay, so you wind up with kind of this mess. You can also do this on the lattice, and you'll get a small sigma naught, but you'll also get a small sigma pi n, which doesn't agree with data. So this is obviously a big problem, even if you're not doing this strange quark mixing. Okay. So that's sort of demonstrated in this table. So the first two rows are your first and second generation nucleon form factors. On the left, you have small strangeness content, right, which is a situation where sigma naught is close to sigma pi n. On the right, you're going towards large strangeness content, so you have a small sigma naught. Okay. And you can see that for first and second generation, you sort of run into 10% differences in your form factor. But for, if you're just going through strange squarks, you run into order of magnitude size differences, depending on whether you're looking at a large strangeness content or a small one. As I mentioned, you can scatter through heavy quark loops and couple with the gluon content of the nucleon. But because we're not in minimal flavor violation, our matrix elements aren't going like mq squared. So it's just a straight gauge coupling. And so you wind up suppressing all of these heavy flavor quark contributions by the quark mass squared in the cross section. So the point of all this is that we have to go through strange quark mixing, and the uncertainty is huge because of these strangeness content uncertainties. So you can just calculate the scattering cross section. This is just a well-known expression for left-right Stark exchange. But as I said, it's proportional to some gauge coupling and the mixing angle. And you have to have non-degenerate masses, or else this will just go away. We also want to check dipole moment contributions. So if you have this kind of mass hierarchy, which is really what we consider, you get a dipole moment contribution that's proportional to the same coupling. So then the thing Jason likes to do is write the scattering cross-section in terms of the dipole moment contribution. And then you know that for some dipole moment contribution with a constraint that's larger than for strange quarks, say 10 to the minus 10, Lhc is basically going to rule out this thing anyway. So unlike leptons, constraints on quark dipole moments are relatively weak. So instead of things like 10 to the minus 9 or 10 to the minus 10, you have Lep and Lhc puts you at like 10 to the minus 5. So everything I'll show in the next few plots, dipole moment constraints are relatively not useful compared with direct detection. So if we look at dependence on some parameters and leaving a small strangeness content, we look at this plot in the dark matter mass light squark plane. And the bands are, the gray region is ruled out by Lhc already. The red region is projected 300 days of Lhc data. And blue is projected LZ7. And so one thing you can kind of see right away is that LHC is constraining these squark masses only down at 400 or 500 GeV So if you have a realization of the MSSM that looks like this, direct detection is going to probe higher spark masses than Lhc can constrain for non-degenerate light sparks. Also, one feature on this plot that we're working on now is you get this swoosh shape, right? Because you're kind of running into this light spark co-annihilation region. And so even for dark matter and light sparks at a few hundred GeV, you can actually get your full annihilation cross-section just from spark exchange instead of slug-time exchange. But again, that's in a special region. That plot on the left is given maximal mixing. So we sort of change the mixing angle on this plot on the right. R is just proportional to the sine squared of the mixing angle. But if you look all the way down on the left, even for mixing parts at 100, you still have LZ7 sort of probing this TeV scale spark mass range. And then as you increase the mixing, you sort of even go into spark mass areas that aren't going to be ever kinematically accessible for LHC, right? So again, in models like this, it's sort of interesting that you can just probe these heavy spark masses. That's a very qualified sort of statement, because the MSSM has to look like this, but I think it's interesting nonetheless. So if you go from the minimal strangeness content, which is this bottom line, and you let it sort of vary with the kind of uncertainties that I discussed, you get a plot like this. So this is just the normal reach plot you have for direct detection. Again, you have Lhc, 300 days of Lhc, and LZ7 projections. And the bottom line here is the minimal strangeness content. This top green band is if you have a large strangeness content, and then the dark green is just if you vary sigma pi n in the 2 sigma range, right? So that's already a pretty large uncertainty. But the huge difference comes from the strangeness content, right? Because that takes you over this 2 orders of magnitude in your scattering cross-section, right? So the strangeness content is usually the biggest uncertainty in calculating your scattering cross-section without this spark exchange scenario. And here, it's just extraordinarily important, right? Depending on what your dark matter mass is and what you want to see and rule out. So the last thing I'll talk about, change gears a little bit and talk about decaying dark matter, decaying multiple component dark matter. But first I'll sort of talk about what scenarios you typically look at and why in single component dark matter you look at these constraints from the early universe. And then I'll sort of compare it to what we talked about for multi-component dark matter, and then as an example, I'll just talk about light elements. So these constraints, I'll talk about these in a second, come into play when you have long-lived particles but not hyperstable, right? So things that aren't giving you your relic density. So something that arises in the MSSM is if you have a neutrally on LSP in a situation with gravity-mediated SUSY breaking, you wind up with a weak scale Gravitino. And it's going to be long-lived because its interactions are suppressed by the Planck mass. So if you wind up with anything that's older than a few minutes, it can run into these constraints, right? So this blue blob is light element abundances, right? This is the plot of decay lifetime versus a lab fraction of the current dark matter density, so abundance. These curves are from CMB ionization history, starting at around recombination. Purple is from structure formation, and then right at the age of the universe, these are direct detection constraints. Okay, and then this is just for some typical cases to give you an idea. Dynamical dark matter is a situation where you have a whole bunch of decaying particles, and I'll have a picture in a couple slides. But the gist is that you have a few fields that live over here and supply your relic abundance. But the existence of these guys basically implies the existence of some other fields with much shorter lifetimes that can impact these kind of constraints. Right. So in the MSSM case, right, again, these are just some canonical cases in the MSSM and M-Supra. But if you look at your Gravitino mass versus lifetime, again, if you get around the weak scale with your Gravitino mass, this starts pushing your lifetime up past a few minutes, and you have to start caring about these constraints. And so you get figures like this one on the right, where, again, if you're past the weak scale, you're pushing your lifetime down before BBM, so you don't have to worry about it. But as you bring it down, you start running into constraints from all these different light elements. And so this is plotted versus upper bound on the reheat temperature, which if your gravitinos are produced thermally, is proportional to the gravitino abundance. So this is gravitino mass versus reheat temperature, but you can think of it as, you can translate that into lifetime versus abundance, like the blue blob. Dynamical dark matter, right? So like I said, you wind up with your more abundant, longer-lived things making up your relic abundance, and they're still around today. Right? This dashed line is today. This is past today. Okay. But you have some less abundant. Right? This is abundance on this axis. Right? Things that are decaying at these dots earlier in the universe. And if it's during radiation domination, that's typically the window for affecting light element abundances. So just a simplified